Hello, everyone. Welcome to Physics 213. This is Lab 6, which is the second of the two labs on rotational equilibrium. And this one is going to deal with applications. So one of the applications that we're going to look at is when performing, and this is going to be done with a human arm model, like a mechanical model, and also an individual's actual arm. When performing an isometric contraction, when you're holding the forearm at 90 degrees relative to the upper arm, we want to predict what the biceps force is by using rotational equilibrium. And then on the mechanical model, we'll measure that force. Basically, it's represented by this tension in the string here, just represent the biceps force. And then we'll compare to what we predict using our model, using our mathematical model. And then the second part of or really the second application is going to be looking at or measuring the center of mass of the human body. So we're going to use rotational equilibrium to calculate the center of mass of the human body, and then we'll compare across gender as well. We'll do this for one male and one female in the class, and we'll compare across gender. Okay, now just like some of my other video lectures, the original video that I created for this lab was recorded basically a year and a half ago, maybe 2 years ago, during the height of the pandemic. So just recognize that the numbering might be slightly different. I think in some semesters I called it 5B. It was also used for my physics, movement science, and sports physics lab. So it was also used for lab physics 206 and 207. So the numbering might be different. The numbering of the questions could be slightly different, but the information is exactly the same, okay? And the other thing you'll notice is when you watch the video that many of the tables have data filled in, because during the height of the pandemic, students couldn't collect data on their own, so I had to pre-collect all the data so that students could analyze it, right? But the information is exactly the same. So the video that follows will describe applications of rotational equilibrium. Great, thanks. Hello, everyone. Welcome to Physics 206 and 207. This is Lab 5, Part 2. And in this part, what we're going to do is we're going to look at a few applications using rotational equilibrium and torques. So the first application is, and we're going to do this both with a model, a human arm model, which you can see here, this like mechanical model, and also with the actual human arm. Think of this as you're performing, or in this case, the model is performing an isometric contraction where they're holding a load in the hand. There's one elbow flexor acting here. So basically it's the tension in this rope. You can think of this as like the biceps force. And what we want to do is if we increase the load in the hand, how does that affect the biceps force while you're performing this isometric contraction? So that's one thing we're going to look at using this model, right? How is that force, that biceps force, changed by changing the load in the hand? So first of all, if you look at this, this again is like what we typically call a mechanical model or like a functional model. It's not an anatomical model where we're trying to match everything exactly. So the first thing I want you to do, the first question, is compare this mechanical model with your actual arm. What are some similarities and what are some differences? Just mention some similarities and some differences. You know, 1 or 2 each would be fine. Okay, now assume that you are holding your upper arm vertical, right? Your forearm is a 90-degree angle to your upper arm, just like that mechanical model was. Now assume that you're holding a weight in your hand, right? And performing an isometric contraction. So there's no motion of your arm, just holding it. So question 2 is what muscle or muscles would you use to resist the load in your hand? Right, so you want to make sure you answer that. And in question 3, assuming that the biceps, and we'll talk about this later, we can only assume there's one muscle acting. I know there's several muscles that span the elbow joint, but let's assume that the biceps is the only muscle spanning the elbow joint. Assuming that the biceps is the only muscle force that acts as an elbow flexor, if you increase the weight in your hand, the weight of the load in your hand, how will it affect the biceps force? What do you think? Do you think the force will increase, stay the same, or decrease? And then we will look at the model. We'll actually perform this experiment and see what we get. But I just want you to predict what will happen. So as you increase the load in your hand, does that biceps force increase, decrease, or stay the same? Okay, now I want to actually go to the iPad and let's actually draw out a free body diagram which represents the forearm and hand, and we will actually derive an equation that gives that muscle force, the biceps force, in terms of the weight of the object. So I'm going to do that next. Okay, so let's assume, to keep this simple, I'm just going to draw the forearm and hand as a line. So this is my forearm and hand. I have my upper arm, right, which will be something like that. So this is going to be the elbow joint here. And then what are the forces acting? Well, the forearm and hand itself has a mass, right? So there's going to be a gravitational force acting at the center of mass of the forearm and hand. So I'll draw that, say, right here. So that's the center of mass of the forearm and hand. So the force acting downward is going to be the weight of the forearm and hand. Then let's assume the object is in the hand here. So this is a hand. So I have the weight of the object pulling downward. And then we have some type of muscle force, right? You can think of it as the biceps, even though in reality, we know that there's several muscles that span the elbow joint. But in order to solve this problem, we have to assume there's just one, or we can kind of lump them together into one muscle force. So let's assume there's one muscle force acting, I don't know, something like this. So this would be, I'll call it FM for muscle force. And then there's one other force that may not seem as obvious, but there's a joint reaction force, right? There's a force at the elbow joint itself. So basically it'd be the force of like the humerus on the ulna, right? There's some joint reaction force. I don't even know what direction. I guess it'll be going something like this. I'm just going to draw it like this. It doesn't really matter. So something like that. Okay. So if the individual is performing an isometric contraction, right? So the forearm and hand is not moving at all. Therefore, if that's true, we know that the forearm and hand is in rotational equilibrium. So therefore, the sum of the torques about any point we choose has to equal, I'll put 2.0, has to equal 0. All right, so the sum of the torques about any point that we choose has to equal 0. Because I don't know anything about the joint reaction force, I really don't want that torque due to the joint reaction force to appear in my equation. So I'm going to put my axis of rotation, right, the point at which the torques are summed about, to be right at the elbow joint. So this is going to be, I'll do it in red. That's going to be my axis of rotation. Okay, then FJ, since it passes right through it, right, its line of action is right through the axis of rotation, it's not going to contribute a torque about that point, which is nice because we don't know what FJ is. Okay, so I know the forces. Now I need to figure out the moment arms, right? So remember, the moment arm is going to be the perpendicular distance from the line of action of the force to the axis of rotation. So if I start with like the weight of the forearm and hand, this is the line of action of the force, right? The line along which it acts. And then the perpendicular distance from that line of action to the elbow joint, right? The axis of rotation is this distance right here. So that's going to be, I'll call it D, forearm and hand. D for like distance, but it's really the moment arm, right? The forearm and hand. Okay, what about the weight of the object? Well, this is the line of action of that force. So the perpendicular distance, right, is just this distance, this horizontal distance. So let me do that in blue again. This is going to be I'll call it DO. So that's the moment arm for the weight of the object. And then finally, the muscle force, this would be the line of action, something like that. So the moment arm is going to be this distance. I'll do it in green. Here, it's a perpendicular distance. So that value, that length, call it dm, that's going to be the moment arm for the muscle force. Okay, now that I have all my forces and I have the moment arms, I can compute the sum of the torques about the elbow joint. So let's do that next. So I have, we know that the sum of the torques about the elbow joint has to equal 0. So I have a torque due to the muscle force, plus I have a torque due to the weight of the form and hand, plus I have a torque due to the weight of the object, plus a torque due to the joint force. That's going to equal 0. And we already know, because the joint force passes right through the elbow joint, this is going to be 0 itself, right? Remember, torque, just to remind you from the previous lecture, the torque is either going to be positive or negative, right? And it's the force, the magnitude of the force times the moment arm. Okay, so what is the torque due to the muscle force? Well, it's going to be the muscle force times the moment arm, which remember we call dm. And then how do I figure out the sign, whether it's positive or negative? Well, if you imagine that the muscle force is the only force acting, right? That we're only force acting, how would it rotate the forearm and hand? Well, about the elbow joint. So if you pull on that, right, then this is going to rotate in this direction. It's going to rotate counterclockwise. Therefore, by definition, counterclockwise is a positive torque. Right, so here, let me remind you of that. So remember, positive is counterclockwise. And negative is clockwise. So this is going to be positive Fm times dm. Okay, then I have the torque due to the weight of the forearm and hand. So the force is the weight of the forearm and hand. The moment arm was d forearm and hand, right? And then since that, if you imagine that this is the only force acting, right, the weight pulling down, how would it rotate the forearm and hand? It'd rotate it clockwise. So this is going to be negative. And then finally, I have the weight of the object, right? So I want the torque due to the weight of the object. So it's the weight of the object times the moment arm of the object. And that would also cause a clockwise torque. So that's also negative. And that's all going to add to 0. So notice what I can do here is I can solve this for the muscle force. I can solve it for Fm. Okay. In fact, if you do that, basically you just move the other two terms to the other side and divide by dm. So the muscle force is going to be the weight of the forearm and hand times the moment arm of the forearm and hand plus the weight of the object times the moment arm of the object, all divided by the moment arm of the muscle. So that's going to be an important equation that we're going to use several times for this part of the lab. Okay, now there's another way I want to write this. Remember, ultimately, when we look at that mechanical model, we want to determine what's going on, like what's happening with the muscle force as we change the weight of the object that's in the hand. So I can write this equation another way so I can see that relationship more clearly. So I'm just gonna, it's the same equation, I'm just gonna rewrite it in a slightly different way. So I'm gonna write this as, let me go back to this color. So F of M is equal to, so I'm going to write this as dO over dm times the weight of the object plus, and then d forearm and hand over dm times the weight of the forearm and hand. Same exact equation, right? I just rewrote it a slightly different way. Why do I want to write it like this? Because this now has the form, right? This has the form y equals mx plus b, where the X, the input, is really our load in the hand, right? This is like the load in the hand. And the output, the Y, is our muscle force, right? The biceps force. So that means the M, we can see the M here, is simply going to be the ratio of the moment arm of the object to the moment arm of the muscle. And then the B, which is related to the y-intercept, that's going to be the ratio of the moment arm of the forearm and hand divided by the moment arm of the muscle times the weight of the forearm and hand. Okay, so at some point you're going to be asked for those two things, but again, you can just pick it out, right? The M here has to be the ratio of the moment arm of the object to the moment arm of the muscle, right? Because it's a coefficient of the weight of the object. So it's the thing that's multiplying the weight of the object. And then the B here has to be that constant term at the end. So this is the ratio of the moment arm of the forearm and hand to the moment arm of the object, to the moment arm of the muscle times the weight of the forearm and hand. And that's basically our y-intercept. Okay, so again, we're going to use this, both forms of this equation in our lab. All right, let me go back to the lab handout. Okay, so in this table, the first column here, these are the masses of the load in grams that I placed in the hand of that mechanical model. So 25 grams and 45, 65, all the way up to 185 grams. So basically, if you go back to that picture, instead of attaching to the end, I just basically hung them from like a little hanger. So I put 25 grams, then 45, and so on, right? Hung it from the hand. And at the same time as I did that, I recorded what the force was from the sensor here. Remember, this is the blue force sensor. So that's measuring the tension in the string. So it's basically measuring the biceps force here in newtons. So if you go to the table, the last column here are those forces that are recorded in newtons, right, from that force sensor. So this is like the biceps force in newtons. All right, so question 4. First thing I need you guys to do is you need to find or calculate the weight of the load in the hand. We know the mass of the load in kilograms. Now we want to know the weight of the load in newtons. Well, that's no problem, right? Because remember, to figure out the weight of something, it's just going to be equal to mg, right? Mass times the acceleration due to gravity. But you have to make sure you're in the right unit. So the mass has to be in kilograms, and then g will be 9.8. So you have to first convert 25 grams to kilograms. So you could either divide by 1,000 or move the decimal place 3 places to the left, right? So it's basically 0.025 kilograms times 9.8. So this first value here is going to be, or second value, the first value is going to be 0, right? And when the mass is 0, the weight of load is 0. Second value here will be 0.245 newtons. So just calculate all of these. We want the weight of the load in newtons. All right, once you have that, then you're going to do, this is question 5, you're going to do a plot. So in capstone, you're going to plot weight of the load on the x-axis. So this is x, and biceps force on the y. Right. So remember, we just derived that equation, which gave the biceps force in terms of the weight of the load. Like the weight of the load was x, the input, and the biceps force was the output. Right. So we're going to do that plot. Once you do that graph, right, make sure you include it in your lab report. I want you to record, perform a linear fit, and then record the slope and the y-intercept. Okay, based on your graph, just by looking at your graph, explain qualitatively the relationship between the biceps force and the weight of the load. Like as the weight of the load increased, what happened to the biceps force? Right. And we already know, since I'm asking you to do a linear fit, it's going to be linearly related, but is it increasing? Is it decreasing? Is it staying the same? So as the weight of the load increased, what happens to the biceps force? Okay, question 7. This one I basically answered for you, and you could give the same answers that I gave on the iPad when I was explaining that equation when we rewrote it. What does the slope represent? Well, remember, the slope, this value right here, should be the ratio of the moment arm, right, of the object to the moment arm of the muscle. And then what does the y-intercept represent? Well, it's going to be the moment arm of the forearm and hand to the moment arm of the muscle times the weight of the forearm and hand. Right? And we derived that earlier. So you just want to explain that. This is question 7. Question 8. Why is there still a biceps force greater than 0 newtons when the load in the hand is 0 newtons? So if you look at this first row here, right? The weight of the load is 0, but I'm still getting a biceps force, 3.49. Why is this not 0? So you want to make sure you explain that. Okay, and then going back to that free body diagram that we drew of the forearm and hand. Now we're going to plug in values. Okay, so assuming that the mass of the forearm is 0.1 kilograms, right? That of that mechanical model, so that metal form, let's say it's 0.1 kilograms. We want to ultimately calculate the muscle force when there's a load of 185 grams in the hand. So let me show you how to do that. It's basically the same thing that we just did, except we're going to plug in values now. So let me go back to the iPad to show you this. Okay, so this, again, I'll just draw the forearm and hand as a line just to make it easier. So this is my forearm and hand, my elbow joint. I have the biceps force. So the muscle force. We have the weight of the forearm and hand. We have the weight of the object. And we also know, we're told that the mass of the forearm and hand is 0.1 kilograms, right? So we know that the weight of the forearm and hand is going to equal the mass of the forearm and hand times, oops, there should be H here. So mass of the forearm and hand times G. Right, weight is always mg. So we can compute that, right? It'll be 0.1 times 9.8. So that'll be 0.98 newtons. So that's the weight of the forearm and hand. We're told that the weight of the object, right? Well, we know it's equal to the mass of the object times g. And the mass that we want to use is the one that was 185 grams. So in this case, it'll be 0.185 kilograms times 9.8. So that'll be 1.813. We also know, we're also given the moment arms, right? So the moment arm, remember this is the line of action of the weight of the forearm and hand. So this distance right here is the moment arm. Well, we're going to be told, so D forearm and hand, that this value is 0.14 meters. Okay, then we have, well, this is the line of action of the weight of the object. So this is going to be the moment arm from here to there, the horizontal distance, right, from that line of action to the elbow joint. And we're told that that DO is 0.35 meters. And then we also have the line of action of the muscle force, so something like that. So that means this distance, the perpendicular distance, that's going to be our DM, right, moment arm for the muscle. And in this case, it's going to be 0.045 meters. Okay, so we're given all those values, 0.045. It's basically like where the rope attaches relative to the elbow joint, right? The perpendicular distance. Or in a real arm, it'd be where the tendon attaches relative to the elbow joint, right? The closest perpendicular distance there would be the moment arm. Okay, so using all this information, now we can calculate the biceps force, right? By using the fact that the sum of the torques about the elbow joint has to equal 0, right? So you're just going to use the same equation as before. Remember, we derived this. The muscle force, biceps force, should be the weight of the forearm and hand times the moment arm of the forearm and hand plus the weight of the object times the moment arm of the object, all divided by the moment arm of the muscle. So using all the information, you want to calculate that muscle force, right? The biceps force. Okay, so think of this as like your computed value. So that's your computed muscle force. All right, let me go back to the handout. Okay, so that value that you just found, and you should show me all the calculation, the entire calculation. Show me the free body diagram for question 9. Show me all the values, just like I did on the iPad, and calculate the muscle force, and that value is going to go here. That's computed biceps force. Now, what is the experimental biceps force? Well, that's the value that we actually got from in a table when I did this out. When the mass was 185, this value should be 16.15, right? The biceps force was 16.15. So when the load in the hand was 185 grams, that was the muscle force, the biceps force. So that value is just going to be 16.15. So you can just write 16.15 here. And then I want you to compare these two by computing the usual percent experimental error, and make sure you show me that calculation, right? The percent error calculation. Think of the computed as being the accepted one. So when you compute the error, right? Remember, it's the difference, absolute value of the difference divided by the accepted. So just divide by the computed times 100. Okay, so that's it for the mechanical model. Now, I want to look at something very similar. So we're going to do the same isometric contraction holding the object in the hand. But in this case, we're going to use a human arm, right? So I just got some data from a subject. And the question is, how do I figure out all these parameters that we need, right? We need to know the moment arm of the forearm and hand. We need to know the moment arm of the object. Some of these things I can measure. So the moment arm of the object, I can measure the distance with the tape measure from the elbow to where the object is, right? The center of the object. But the other values I have to get from tables, right? And basically what I did was I used information from cadavers. So I can figure out the mass of the forearm and hand as a percentage of the total body weight, or you could do the weight of the forearm and hand as a percentage of the total body weight. Or I can figure out the moment arm of the forearm and hand as a percentage of the length of the forearm. So I can maybe measure the length of the forearm from the elbow to the wrist. And then using cadaver data, I will know the percentage where the center of mass is going to lie. So I can get the moment arm for the forearm and hand. So basically for this part, we used cadaver data to get a lot of the data. Okay, I collected some of it. The other information is going to come from cadavers. So if we look at, this is the same exact model as before, right? The same mathematical model. Let's go to the table here. Okay, so these are the values in the table that I collected for you. So the weight of the person, we're going to put as 1,001 newtons. The length of the forearm, so that was the distance, and you can see all the definitions here. So the length of the forearm is from the elbow axis, the elbow joint, to the wrist. So I measured that in centimeters and converted to meters. So that was 0.28 meters. So given that information, we now want to calculate the weight of the forearm and hand. Well, based on cadaver data, it turns out it's around 2.2% of the person's body weight. So to find the weight of the forearm and hand, all you're going to do is use 0.022, right? That's 2.2%, 0.022 as a decimal, times the weight of the person, times 1,001. And that'll be the weight of the forearm and hand in newtons. The weight of the object, well, it was a 2 kilogram object, right? So I just multiplied by 9.8 to get 19.6 newtons. So that's given. To find the moment arm of the forearm and hand, this again was cadaver data. It turns out it was 68.2% of the length of the forearm. Remember, we measured the length of the forearm to be 0.28 meters. So if we do 0.682 times that value, that's going to be the moment arm of the forearm and hand. The moment arm of the object, I just measured from the elbow joint to the object in their hand that they were holding. And that turns out to be 0.36 meters. This is not easy to get, right? Because how, like, you could maybe do it if you had X-ray data, but it's going to vary with subjects. So I just chose sort of an average value. So we're going to say that the moment arm of the biceps muscle is the same as it was for the mechanical model. It's around 0.045 meters, right? Remember, this is like the distance from the tendon to the elbow joint, that moment arm. Okay, so given that information, here's what you need to do. You need to, first of all, you need to calculate these missing values here. And then ultimately, you want to calculate the biceps force using the same equation that we've been using, right? So calculate the biceps force. And then there's one other question here, question 12. How does the force of the biceps muscle compare to the weight of the object? So when you calculate this in newtons, how does it compare to the weight? Remember, you were holding 19.6 Newton weight in the hand. Is it about the same? Is it like 2 times as large? Is it half as large? Is it, 20 times as large? So if you just write it as a ratio, if you do the biceps force, muscle force, divided by the weight of the object, divided by 19.6, that'll tell you, it's 3 times as large or 1/2 as large or 10 times as large. So I just want to get that particular answer. How many times as large is it as the weight? Okay, so it's very similar to what we did with the mechanical model, except we used the real human arm, and then we had to use cadaver data to get these, to get the weight of the forearm in hand and the moment arm of the forearm in hand. All right, then there's one last part here. So in this part, we're going to determine the location of the center of gravity of the human body relative to the person's feet. So like if you're standing up, it'd be how far up from the floor your center of mass is, your center of gravity. So relative to their feet. So let me explain how we do that. And we're ultimately going to come up with this equation that gives that position. The Z here is the distance from their feet to the center of mass. So we want to come up with an equation that gives that value for Z. All right, so I'll do this on the iPad. Okay, so basically, here's what's going on. We have this board. It has these like 2 little knife edges, just pieces of angle iron. And one side is going to be on a scale. So let's say this is a scale. And the other side is just on a block, right? A block of wood. And then the individual is going to lie down. So something like this, where their feet are at the right knife edge. And then measuring the force on the scale, right? The force that the scale reads when they're lying down like that, we're going to be able to estimate the position of their center of mass. Let's say their center of mass is right there, okay? So first thing, let's draw all the forces acting on, basically we're going to consider the system of the board and the person to be one object, right? So all the forces acting on it. Well, we know here the scale on the left knife edge, the scale is exerting a force upward on that left knife edge. So I'm going to call that F. On the right knife edge, same thing. The block is exerting a force on that right knife edge. I'm going to call that P. Then we have the weight of the person. Well, that acts at their center of mass, right? So that's down, straight down towards the center of the earth, weight of the person. And then the board has a weight. And as long as the board, doesn't have a ton of extra nails or screws on one side, it's pretty much symmetrical. We're going to say that the weight of the board acts at the center of the board. So something like this. This would be like the weight of the board, right at the center. Okay, now, when the person is lying still like that, right, the board and the person are still, then they're in rotational equilibrium. So I know that the sum of the torques about any point I choose has to equal 0. But there is a point that I really want to use here because I can measure F, right? I can measure this value right here, F, because I can read the scale when they're lying down. I can measure the weight of the person. I can just weigh them before they get on the board, and we can weigh the board as well. So I know those 3 forces. I don't know anything about P here, right? I don't know anything about that force. because I can't measure it. I don't have a sensor there. I don't have a transducer there or anything to measure that force. So I would like P not to appear in my torque equation. I don't want P to appear in my torque equation. So where can I put the axis of rotation so that P does not appear in my torque equation? Well, remember, right, if P passes through the axis of rotation, then it doesn't contribute a torque about that point. So why don't we put our axis of rotation right at the right knife edge, right here? Then P will not contribute a torque about that point, which is nice because I don't know anything about P and I really don't want it to appear in my equation. Okay, now that we have the axis of rotation, let's figure out all the moment arms. Well, the force that the scale reads, F here, this is the line of action. So that means the moment arm is simply going to be this. See if I can fit it in here. It's going to be this distance from here to here, right? The horizontal distance. That's just the length of the board, right? So give that a name. I'll just call it L, I guess, in this case. So this is L. So it's basically the length from knife edge to knife edge, right? Then the weight of the board, this is the line of action of that force. So the perpendicular distance is again going to be just from the weight of the board to the right knife edge. And that's basically half the length of the board. So that's going to be 1/2 L, or right as L over 2. And then finally, the weight of the person, this is the line of action of the force. So the actual moment arm is simply from that to the axis of rotation, right? That perpendicular distance. So I'm going to call that Z. And ultimately, that's what I want to find, right? Because Z is giving me the distance from their feet to their center of mass, right? So it's how high up their center of mass is relative to their feet. That's what ultimately we want to find is Z. Okay, so let's do the sum of the torques now. So I have a torque due to the force F. I have a torque due to the weight of the person. I have a torque due to the weight of the board. I have a torque due to P. That's going to equal 0, right? The sum of the torques about that rotation point has to equal 0. And since the force P passes right through the axis rotation, it doesn't contribute a torque. So we already know that one's 0. Okay, what about the other one? So torque due to F. Well, it's going to be the force F times the moment arm, which is L. And notice here that if that were the only force acting, right? If this is the only force acting, how would it rotate the board and the person? It'd rotate it clockwise, right? About the rotation point, it rotate clockwise. So that means this has to be negative. Then I have the weight of the person times the moment arm, which was Z. And how would that rotate it? Well, if that were the only force acting, it would rotate the whole thing counterclockwise, right, in that direction. So that's going to be positive. So this is plus. And then finally, I have the weight of the board times the moment arm, which is L over 2. And that torque is also positive because it would tend to rotate it counterclockwise. And that's got to equal 0. Okay, now let's solve this for Z. Okay, so solve for Z. So here we need to do a little bit of algebra, right? I'll add FL to both sides. Start with that. So I'm going to get weight of the person times Z plus, oh, this should be a B here, right? Weight of the board plus weight of the board L over 2 is equal to FL. Remember, I want to solve this for Z. Now I need to subtract this term, right? Weight of the board times L over 2. Weight of the board times L over 2. So I'm going to get weight of the person times Z is equal to FL minus weight of the board over 2 times L. And then finally, I can divide by the weight of the person. So I'm going to get Z is equal to FL minus weight of the board over 2 times L over the weight of the person. And just to clean things up a little bit, in the numerator, I could factor out the L. So I could write this as, it's F minus the weight of the board over 2, all times L, right? Factor out an L, divided by the weight of the person. And that's the formula we want to use to figure out the location of the center of mass, like the vertical location from their feet. How high up in their body is their center of mass? That's going to be the Z. It's kind of a funny set of units in this lab. The Z is going to be in inches. And the weights, because that scale is an old scale, we had to measure the weights in pounds. But then it's okay, as long as we're consistently using, the correct units, the Z will end up being in inches. Okay, so that's the equation you want to use. So let's go back to the handout. Okay, so for this, I found some old data that I had from 2 students. So typically we choose one male and one female, so we compare the locations of the center of mass later. So we did that, right? Weigh the person because we need WP. We measured their height, right? And that's going to be in inches, so everything's consistent. We know the weight of the board is 32 pounds. That's given to you. And we know the length of the board is 79 inches. That's given to you, right? So the only thing that we needed to measure was that force F that the scale exerted on the left knife edge while they were lying down. And that value is in the table. So I have all the values in the table here. So this is for the male subject. This is for the female subject. So what I want you to do is to calculate Z. So you can use that same equation to calculate Z for the male subject and for the female subject. Remember, that'll be in inches. All right, so this is basically question 13. So calculate Z, and then because we want to compare gender, we now need to represent Z in a relative way, so like as their percentage of height, because if we just compare the absolute Z's in inches, the difference may be due just because one individual is taller than the other, right? It may not have anything to do with gender. It may just have to do with the fact that they're taller. So if we represent them as relative measures, so to figure out this value, and this is the last part of question 13, you simply have to take the value Z that you found divided by their height in inches and then times 100, and that'll be a percent. Like it might be 55% or whatever you get. It'll probably be 50 something percent. And the same thing for the female subject. So it'll be her Z in inches divided by her height times 100, and that'll be Z as a percentage of her height. And the last question is, were there differences between the male and female subjects? So by looking at the answer here, especially the relative measure, Z as a percentage of height, were there differences? Okay, and then does that make sense? Right, was one a greater percentage than the other? And what do you know, like if you think about the general population, right, do you think males or females typically have a, let's say, lower center of mass or center of gravity, right? So you want to think about that. Now, of course, it really depends on the individual, right? It really depends on the individual, but if we look at the total population, there is a general trend, okay? So once you figure that out, you want to answer that question, question 14. All right, that's it. So again, the whole purpose of this lab was to at least show you a few applications of torque, like why torque is important, right? We can use it to estimate muscle forces. We can use it to locate the center of gravity of the human body. It really is an important topic in physics, especially if you're studying things like exercise science or physical education or, athletic training or PT, because you will encounter these things, right? So this concept is very useful. All right, great. Thank you.